Okay, now that we have these differentiation formulas, we certainly would like to see them in action. And the first thing we're going to talk about here is the graphing of functions. Now, that is a topic where people can, with a bit of good reason, say, well, yeah, we have computers to do that for us now. But at the same time, there's a number of good reasons as to why we would want to graph functions by hand. And, well, some of those reasons are listed on this slide that tells us what we gain from graphing. First of all, and I consider this really very important, graphing teaches us to process information in a structured fashion. And even though that is correctly classified as something that is very schematic, there's an awful lot in the working world that is simply schematic. And even though I'm not a tax consultant and will not give advice on these things, doing my taxes and anybody doing their taxes is one of those examples. It is neither fascinating nor thrilling, but you just have to process the information that you have for your taxes in accordance to the structure that is given by the tax law and by the forms that you're getting. And if you do that, you fill out your forms correctly, and the government will not be bothered by you not paying enough taxes, and you will also not feel like you've paid too much because you've just been in accordance to the law, and in the process, you may have saved the money that you would need for a tax advisor. Other things in the working world where you simply have to be structured, even though it doesn't sound like it's terribly creative, is something like workplace safety. I am not personally working in a lab, but because I'm working with engineers, safety is a topic that comes up every so often in our administrative meetings. And, well, it is very routine, it seems. It is very schematic, but for goodness sakes, whatever safety regulations there are, we simply have to follow them in a structured fashion because we don't want anybody to get hurt in the workplace. So whenever people say something is terribly schematic, yeah, they may be right, but we have to get it right anyway, and the only way we can guarantee that, or get as close as possible to guaranteeing that, is by learning how to process information in a structured fashion, how to follow an algorithm. And that's what we're doing here. Okay, another thing that is often discounted is manual dexterity. And for just about anything that engineers and scientists do these days, you will ultimately use computer-aided design in order to draw pictures. I mean, the pictures you're going to see in this presentation are created on a computer. But it helps in communication, in day-to-day communication, to be able to draw some pictures. And along those lines, then also this manual dexterity also helps your visualization skills, because all those pictures that I now create with a computer, they first had to exist in my mind, and some of those pictures I even had to sketch out with a pencil first to really figure out where I wanted to place the various lines to get a picture that actually communicates the information that I wanted to communicate. And that is something where I don't think many engineering curricula still require a full class in design, in graphing. In fact, there might not be any curricula out there like that anymore, but that manual dexterity is still needed, at least at some level. You probably don't need a full class in just doing technical sketches, but some manual dexterity helps a great deal, really. Finally, then, or not finally, but next, as we're going through a fairly complicated but structured process, you also gain experience with finding and eliminating errors if your data becomes contradictory. Of course, the ideal situation is you don't make mistakes and you get things right, but if things become contradictory, that's when you learn how to troubleshoot, and that's a very important skill to also have in the workplace. And how do you troubleshoot? Well, you've got to be familiar with the process, and once you are familiar with the process, you develop an idea as to where things could go wrong. It also prepares us for things in mathematics, because ultimately we'd like to analyze family of functions and multivariable functions, and that's where the sketching isn't so easy anymore, and that's where also just getting a multivariable plot sometimes doesn't give you the same familiarity with the functions as you would get by working out a by hand sketch that just does things on a more conceptual level. And we'll have a separate presentation on sketching families of functions that involve a parameter. And finally, my personal experience there, it's brain training. It's making you use things. It's making you use knowledge that you should be able to activate anyway. So I consider it better than any kind of brain training software that you can buy for your computer, your cell phone, your game console. Who knows, at some point in time, they'll probably put it on a toaster too. Okay, so now enough of the sermon, let's get to it. The graphical features that we can determine with computation, there are actually quite a few of them. We can determine the growth behavior, and remember that means derivative positive is increasing, derivative negative is decreasing. That's the kind of thing you want your mind to pretty much flash to when you think about growth behavior. You want to talk about concavity. That means second derivative positive is concave up, second derivative negative is concave down. Again, that's the kind of mental connection that you want to make as soon as concavity is mentioned. You can talk about y-intercepts. Well, those are algebraic features. Now, y-intercepts and x-intercepts. Well, the y-intercept, there's only one, and x-intercepts, as many of them as there are. You can talk about vertical asymptotes, where you talk about limits. You can talk about horizontal asymptotes using limits. You can talk about vertical tangent lines, places where the derivative blows up. And you can talk about symmetry, and for this course, at least, we're going to be limiting ourselves to whether functions are even or odd. Okay, and here's our task. Here's our example. We want to sketch the graph of the polynomial f of x equals 3x to the fifth minus 5x cubed plus 1. Well, that's quite complicated. It's a cubic polynomial. So how do we go about this? We'll do the computations on this side, and we're going to collect the graphical data on this side. Here's where the limitations of these online presentations come to bear a little bit, because typically I'd like to have all the computations available, visible on as many panels on blackboards or whiteboards as possible. But by structuring it up again, I think we can make this work. So, first thing is growth behavior. For that we need the derivative, which is 15x to the fourth minus 15x squared, right? 3 times 5 times x to the fourth is 15x to the fourth, minus 5 times 3 times x squared is minus 15x squared. The derivative of 1 is 0. And now we set that equal to 0. And of course 15x squared is a common term, so we factor that out. And that's still supposed to be equal to 0, but now we realize 15x squared equals 0 and x squared minus 1 equals 0 are the individual equations, and they're easy to solve. We get x1 equals 0, and then 2 more places where the derivative is 0, namely at plus minus 1. And we do what we always do in our growth behavior analysis. We put this on a number line, and if you work this out on a homework problem, I would recommend that this be a separate page where on the bottom you put the number line for increasing and decreasing. And so you work with f prime, and you have to translate that into knowledge about f. You look at your cut points, which are here, here, and here, -1, 0, and 1. You find checkpoints. Well, there's one here, here, and here, and I would probably take -5/4 here. I want it to be on the scale. I want to encourage you to draw this all to scale. Of course, -5/4 is quite hard to plug in, so I mean, I would check it at -2 maybe. But in between, we even don't have a really good option. -1/2 is just about as close as you can get to a harmless number in between -1 and 0. 1/2 is about as close to a harmless number as you can get between 0 and 1. And to the right then 5/4, yeah, if you use 2 there, that's not a problem. Okay, for the sign check, I think I could think about plugging that in here, but that's a horrible acrobatics, so if I just plug it in here, I think it will go fairly well, because 15x squared, that's always positive, no matter what this number is. Hey, that's great. -5/4 squared, what I know about that is that's a number that's greater than 1, so if I subtract 1 from that, it's still positive, so we get positive times positive. So the derivative is positive from -infinity to -1. -1/2, same story. This part here is always positive. -1/2 squared is 1/4, minus 1 is negative, so that means that the derivative is negative here. For 1/2, we get positive times 1/4 minus 1, which is negative, so we get a negative derivative between 0 and 1 too. -1 also. And at 5/4, again, this part here is positive, and 5/4 squared is greater than 1, minus 1 remains positive, and so we end up with a positive derivative here also, and so our function is increasing, decreasing, decreasing, and increasing. And now we can move on to concavity, and notice here that we're just keeping this information around, and we're going to put the concavity information on top of this. The first derivative was 15x to the fourth minus 15x squared, which means that the second derivative is 60x cubed, 4 times 15x cubed, minus 30x, which is 15 times 2x, 15 times 2x, yeah, okay. And 30x is a common term here. We set that equal to 0. We end up with 30x times 2x squared minus 1. That's supposed to be 0. That gives us 30x equals 0 and 2x squared minus 1 equals 0. which gives us x1 equals 0 and x squared equals 1/2. Sorry about the equal 0 not making it here. So that gives us now that x1 is equal to 0 and x2, 3 being plus minus root 1/2. We work out our number line. We want to talk about f double prime and about f. We have three cut points, 1, 2, 3, which are negative root 1/2, 0, and root 1/2. And we need checkpoints here, 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 and here. And those checkpoints are negative 1, negative 1/2, 1/2, and 1. This time we can actually draw that to scale, and we have got reasonably decent numbers, or as decent number as possible. Let's see. Second derivative at negative 1 gives us negative 60 plus 30. That's negative, so the function is, the second derivative is negative here. Remember, the checkpoints go into the function, the entity that has given you the cut points. And so that means we have to plug our negative 1 into the 60x cubed minus 30x, not into the 15x to the fourth minus 15x squared. Plug in negative 1/2. Let's see, I think I'd rather, well, okay, negative 1/2 cubed is negative 1/8. 60 over 8 is 30 over 4. Negative. Negative 30 times negative 1/2 is 30 over 2. Well, 30 over 2 is bigger than 30 over 4, so that should be positive here. And yes, the function is, the second derivative is positive there. At 1/2, we end up with 30 over 4 minus 30 over 2, so that should be negative. And at 1, we get 60 minus 30. That is positive. Now, do not be unduly impressed by these kinds of mental acrobatics. I still like to train my brain on these kinds of things. And so working these things out mentally certainly is a good exercise. But if that doesn't work for you, use a piece of paper and a pencil, or use a calculator to get those numbers. Well, then translating it again, negative second derivative means the function is concave down. Positive second derivative means the function is concave up. Negative second derivative means the function is concave down. Positive second derivative means the function is concave up. We keep this information, right? In a class, I would just keep this all on a separate panel. And like I told you, you should probably keep this on a separate page, on a separate piece of paper. Now we can talk about algebraic features like the y-intercept. Well, f of 0 is equal to 0. We can talk about the x-intercepts, and those things can be worked out, but it's hard, if not impossible, algebraically, because there is no quintic formula. And so we'll leave that to numerical determinations, and here I think I even left it out. And then we're certainly interested in the values of the function at the points that are interesting, such as negative 1. And f of negative 1 is 3. Well, let's see. We get negative 1 to the 5th is negative 3. Negative 1 cubed is negative 1 times negative 5 is 5. So 5 minus 3 is 2 plus 1 is 3. That's good. We're interested in f of 1. Well, that's 3 minus 5 plus 1. That's negative 2 plus 1. That's negative 1. Sure. We're interested in f of 0. We already have that. The x-intercepts are therefore then between negative 2 and negative 1, if you will, because at negative 2 the function is negative and at negative 1 it's positive. Between 0 and 1, because at 1 it's positive and at 0 it's positive and at 1 it's negative. And then there is another one between 1 and 2, because f of 2 turns out to be positive and f of 1 was negative. And that's as much as we're going to say about that. Vertical asymptotes, well, polynomials don't have vertical asymptotes. Horizontal asymptotes, polynomials don't have horizontal asymptotes. Vertical tangents, well, polynomials don't have vertical tangents. And symmetry, this function is neither even nor odd, so certain parts of the discussion can be dismissed fairly quickly, and there's no problem with that either. And now we're coming to the point where we're plotting points. We already knew that f of negative 1 is 3, f of 1 is negative 1. Then we need f of negative root 1/2, and of course that gets ugly, but hey, we either stick it in the calculator or we grit our teeth and work it out. Basically, this is equal to, well, the negative sign. It's negative 3 times 1/4. Yeah, okay, I tried to time that a little bit more. Times root 1/2. There we go. I tried to, I guess, set that up a little bit more step by step than I was ready to do at this stage. The 3 is the coefficient, negative number to the fifth gives us a negative sign. Root 1/2 to the fourth is 1/2 times 1/2, which is 1/4, and then we've got another root 1/2 because it's a fifth power, and that's the one up here. Similarly, we get a plus because a negative cubed is negative, and with another negative that gives us plus. Then we keep the 5, and then we plug in root 1/2, and that gives us 1/2 from root 1/2 squared times another root 1/2 that is left over, because any x cubed is just x squared times x, so that's how I broke that up. Then you get a plus 1 there, and if you work that out, well, that's a 1 plus 7/4 times root 1/2. Let's see, how does that go? Now you just have to sort out the fractions. 5/2 is 10/4, minus 3/4, that's 7/4. Yeah, sure. And that's approximately 2.2374. Remember, calculators are not the devil's work, but we want to work with our minds as much as possible. And yeah, you want to have a decent decimal here, and it's 2.2374. Same, okay, f of 0 we already had. Working out f of 1/2 goes similarly. This time we just keep the 3, and root 1/2 to the fifth is 1/4 times root 1/2. We keep the negative 5. Root 1/2 cubed is 1/2 times root 1/2 plus 1. And that ends up being 1 plus, well, let's see, this is 10/4, and this is 3/4. 1 minus 7/4 root 1/2. And that ends up, if you want to have a decent decimal, that's approximately 0.2374. And based on that, we can set up our axes. The x-axis should certainly contain the points where some interesting stuff happens, which is at 1/2, between negative 1 and 1. So we're looking at negative 1, 1/2, negative 1/2, 1/2, and 1. Exactly. And the scale on the y-axis should reflect where those points are. So here we'll probably have some more attention paid to the positive y domain, because after all, the points that we're interested in are mostly on the positive side. 2.2 is farther up than negative 1 is down, so that's why the x-axis is a little bit lower than the center here. And so we're marking that negative 1, 1, 2, 3, right? Negative 1, 1, 2, 3. Now we're just going to go ahead and plot points. We've got the point negative 1 and 3. We've got the point negative root 1/2 and 2.2374 right here. We've got f of 0, which is 1, which is here. We've got the point root 1/2, negative 0.2374, which is around here. And we've got the point 1, negative 1 right here. And you can see already there is an advantage to drawing these things to scale, because then the ugly numbers can be projected up, and that's in fact the next step. We're projecting up all the places where the behavior of the function changes, where either the concavity or the increasing decreasing behavior changes. And now we see in this leftmost region the function is increasing concave down, which looks like this. In the next region the function is decreasing concave down, which looks like this. In the next region the function is decreasing concave up, which looks like this. In the next region the function is decreasing concave down, which turns around this way. In the next region the function is still decreasing, but now concave up. And finally the function is increasing concave up. And as I said in a presentation where we didn't have differentiation rules available, well, this is now just basically a set of railroad ties, and we need to use these railroad ties to connect these points together with the behavior that said that the function will have an x-intercept between negative 2 and negative 1, and an x-intercept between 1 and 2, the one between 0 and this root of 1/2 is pretty much automatic. The function will have to cut through somehow. And then for the limiting behavior, there are no asymptotes, but we know a quintic polynomial with positive leading coefficient will come from minus infinity and go off to plus infinity. So we connect that in a concave down increasing, then a concave down decreasing, then a concave down concave up decreasing, then a concave down decreasing, then a concave up decreasing, and finally a concave up increasing fashion. And we have the graph. And this is a graph that we could have also drawn by hand. The computer here only helped me to just draw it to scale just a little bit better, but if you do this very carefully on square paper or an engineering paper, you'll get a very accurate picture. And then the really cool thing is you can compare this to a graph that is obviously created by a computer. And when you do that, you realize, and we just flash back and forth here, you realize we really got pretty much exactly the same picture that we got from the computer. Well, big deal. We could have gotten that picture from the computer a lot faster. Well, but the satisfaction here really is that we can predict the behavior of the system. And the other thing about the graph that we have drawn is the graph reflects the interesting points about the function. The graph tells us exactly where the inflection points are, which are rather hard to find on something like this. And so this kind of flashing back and forth, that's something that I did a long time ago for the first time in a class, and it was actually a surprise to me too that something that I had on an overhead projector with something that I projected off a graphing calculator pretty much exactly matched the chalk picture on the board. And then there's a certain amount of satisfaction in seeing that, yeah, you got that right. So in some ways, I always say, don't look in the back of the book, and I will keep saying that. That doesn't mean that you want to deny yourself the satisfaction of verifying that you've done things right, but you want to do that in a way where you're using a tool that you have available at all times. And this is certainly the case. So remember, I do not say that computers are the devil's work. I am not crazy. I do not believe the machines will rise. My name is not John Connor. Remember from the previous presentation, I am Batman.